Okay, so good morning, good afternoon, or whatever the time may be when you actually get to watch this. I'm Dr. Warwick Belcher, and over the next 10 minutes I hope to give you a demonstration of my teaching skills by introducing you to the wonderful subject of the redox chemistry of metals. Okay, this is the sort of introduction that I might do for either first years or potentially for second year students. So a few learning objectives. By the end of this lecture, I would hope that we will both understand the definition of oxidation and reduction processes and be able to understand what a redox reaction actually is. We will understand what a half reaction is and be able to identify the half reaction potential, E0, and the fact that it can be used as an electromotive force for redox reactions to occur. We're going to look at half reaction potentials and use them to identify oxidizing and reducing reagents and also to predict overall reactivity of redox reactions. And finally, if the gods be willing, we're going to get an example of a metal-based reduction reaction occurring. Okay, so first of all, what is a reduction or redox reaction? So the term redox is basically a combined contraction of the two words reduction and oxidation. And so what a redox reaction then is a reaction in which both a reduction and an oxidation take place. And as such, it is an electron transfer process between species. So if we look at a nice example, for example, the reaction of sodium metal with chlorine gas, we can see that basically sodium metal reacts with the chlorine gas and is converted to sodium chloride, common table salt. It does so with the generation of a lot of energy. Okay, it's quite a spectacular reaction. In doing so, the sodium metal loses an electron from its valence orbitals. So an electron from the 3s orbital gets transferred into the 3p orbitals of the chlorine. In doing so, we form a sodium ion, a chlorine ion, and basically both of the elements end up in stable electron configurations. So there's a driving force for it to occur. The overall process can be considered as two half reactions. We have an oxidation where the sodium loses electrons and a reduction where the chlorine gas gains electrons to form chloride. Okay, and we'll always see this occurring in a redox reaction. Both oxidations and reductions will occur together. There will never be a case where we either generate free electrons or use free electrons from the environment. One of the nice things about transition metals is that they have a very rich redox chemistry. Okay, the interesting thing is that they have both s and d orbitals available as valence electrons. And so as a result, they have the access to multiple stable oxidation states. So if we, for example, consider manganese, we can see that manganese has a 4s2, 3d5 electron configuration in the valence orbitals. That means that there are potentially 7 electrons which can be lost to form cations, okay, and give stable configurations. And we do see that occur. We can see that we can have stable manganese metal with an oxidation state of 0, going through to manganese 2 for manganese dichloride, manganese 4 for manganese dioxide, and finally manganese 7 for potassium permanganate, where we now have lost all 7 of these valence electrons. Okay, and now we form what is, as we know, a very powerful oxidizing reagent. So this ability to have variable oxidation states and to readily interconvert between them is a very common characteristic of transition metal elements. Okay, and these states, these compounds usually arise either from the loss of electrons to form stable cations or from the additional electrons to form the elemental metal itself. So as I said before, redox reactions can be considered as two half reactions, an oxidation and a reduction. Each of these half reactions will have a measurable drive, a potential or half potential which determines the direction of reaction and how powerful that reaction will be. Okay? Conventionally, these reactions, these half reactions, are written as reductions. Okay, and so if we look at any half reaction, for any pair of the reactions, the one with the more positive reduction potential will occur as the reduction. The other half reaction then is going to be reversed and will occur as the oxidation. So what we need to do then is basically balance and combine these half reactions in the right directions to give the full and overall redox reaction, and that will allow us also to determine the total potential for the reaction. So if we consider the two reduction half reactions for the sodium and chlorine case, sodium ions plus an electron go to sodium with a potential of minus 2.71 volts. Chlorine gas plus 2 electrons gives chlorine ions with a potential of plus 1.36 volts. Clearly, this is the more positive reduction potential, and so the sodium reaction will be reversed. And in order to balance the electrons, we'll also multiply it by 2. Okay, now we can simply balance this equation and add it together to give 2 sodium atoms plus chlorine, giving 2 sodium ions plus 2 chloride ions, and an overall potential now of 6.78 volts. And in order to be able to determine these reactions and look at them and work out how molecules or atoms will react, chemists have been kind enough to give us massive lists of basically these half potentials. And so we can see here half potentials for things like fluorine gas being converted to a fluorine anion, which has a high reduction potential, down to lithium ions forming lithium solid with a low reduction potential. Here we have strong oxidizing agents, here we have strong reducing agents, and basically we can take these reactions and their half potentials and predict what overall reaction will occur. So given this knowledge, let's do a little pop quiz. Okay, so if I have copper 2+ reacting with 2 electrons to give copper metal with a potential of 0.3 volts, and aluminium 3+ reacting with 3 electrons to give aluminium metal with a negative potential of 1.66 volts, then when I add aluminium foil to a solution of copper chloride, what should we predict will occur? Okay, so who would think then that no reaction will occur? Okay, who would think then that a solution of copper 2+ and copper 3+ ions will result? Okay, who thinks then that aluminium will dissolve and copper metal will be deposited? And finally, who thinks that the lost city of Relar will rise up out of the sea and Cthulhu, the great elder one, will once again walk the earth? Okay, finally, who doesn't think anything at all? Aha. Well, don't trust me. The answer is the more positive potential will act as it will be reduced, the more negative potential will be reversed, and so we should see aluminium dissolve and copper metal being deposited from solution. Don't trust me though, we should do the experiment and find out. So, stand back, let's do some chemistry. Alright, so let's do a reaction between copper chloride and aluminium. And we'll do it quickly before Cthulhu arises and see what happens. So first of all, I'm going to make up a solution of copper chloride. Okay, so that's 8.5 grams of copper chloride in 50 mils of water. You can see we're getting a greeny solution initially, and then as it starts to dissolve, it'll go more bluey. Nice sound effects. Alright, so now we have our solution of copper chloride. Okay, now I'm going to add 1.2 grams of aluminium foil, and let's see what happens. You can see that we're starting to get a very vigorous reaction. Red material is being formed on the aluminium. And a lot of bubbling is occurring and vapour is being given off. And I've got the right, if the amount's right, hopefully this reaction should go down and stop in a second. Okay, so notice that the aluminium is almost completely dissolved now. The solution has now gone colourless, and we now have red precipitate formed right throughout the solution. Alright, so that was interesting, but what actually happened? Okay, so the first thing that we observed is that we dissolved the copper chloride and we got a green-blue solution. Okay, this green-blue solution is the formation of the solvated copper chloride. So we have 2 chlorines and now 4 water molecules in the coordination sphere of the copper atom, or copper ion. We should have noticed that as that dissolved more fully, we now got a blue solution. Okay, and this is due to ligand exchange with the chloride ions and water. Okay, so now we're going to a copper hexaquo ion. Okay, and now we have chlorine ions floating around solution, and they take no further part in the reaction. They are now simply spectator ions. When I added the aluminium foil, we got a vigorous reaction. Okay, the solvent heated locally on the surface of the aluminium, and we actually see it boiling. Okay, so heat is being generated. We see bubbles forming, and the aluminium starts to crumple and starts to dissolve. The aluminium foil is fully oxidized, and so it goes into solution now as aluminium 3+, and we get a colourless solution of the hexaquo complex. Okay, and finally, we see when I swirl it around that we basically have copper 2+ being reduced and get a nice fine powder of copper, ready copper coloured copper metal now forming in the base. Okay, and so the reaction has occurred. We've taken our copper 2+, our copper metal, our copper 2+ and our aluminium metal. We need to reverse our aluminium reaction. We now need to basically make sure that the number of electrons is the same for each half reaction. And so the lowest common denominator of 2 and 3 being 6, we need to multiply this by 3 and this by 2. And so we get this. And now we can simply add up the reaction. We get 3 copper 2 ions reacting with 2 aluminium atoms to form copper and aluminium 3+ in solution. And so that's basically what happened in that demonstration I showed you. It's a nice example of a redox reaction that occurs readily. So for next time, I want you to go away and actually find out a little bit of information. I want you to read up on zinc sacrificial electrodes. Find out what they are, why they are used in the boating industry, and how what they do relates directly to the chemistry that we've just seen today. Okay, have a good rest of the day, and thank you very much for your time.